Welcome to Chapter 12. I hope you've had a good semester and are looking forward to a good, productive second semester. Chapter 12, as you can tell, is on statistics, one of my favorite topics, and I think that you'll enjoy it too. I always include this because I think it's a good introduction to taking statistics, whether it's Math 101 or Econ 291 or whatever it is. This gives you a little bit of a head start or a jump start on learning some of these things when the pace is a little bit faster and it might be done a little bit different. One thing I might add before we get rolling here is that if you do take statistics, and most of you will, if you need some help, you can always drop by my office or contact me. Remember, sailormath@outlook.com if you need help. I'm very good with the calculator. Any of the Texas Instruments calculators, whether it's a TI Inspire or TI-84, come to me for help. I can really help you, I'm sure. If you do happen to get an instructor that uses the tables, for example, you definitely want to check with me and see if you can do things a little bit faster and easier and better. Okay, here we roll. We're going to look at populations and how we can describe the properties, find the sampling technique, organize the data, present the data. Maybe it's your data or you're asked to present it. Find deceptions. Yes, some people are mini crooks when it comes to displaying data and trying to present it. So we'll take a look at some of the places you ought to look to see whether there's some subterfuge going on. So here we go to statistics. We're talking about collecting, organizing, analyzing, and interpreting data. And we'll get to just a tiny bit of all that. But the main reason for statistics is draw conclusions and find out how we ought to make our decisions. And that method is divided into two main areas. Descriptive statistics, that's when you've already got it. And all you need to do is figure out how you're going to explain what's going on. Or inferential statistics, where you don't have all the data perhaps, but you still need to draw some conclusions. How can you do that with only some of the data possible? Okay, populations versus samples. Population, very simply, contains all the people or objects that you're interested in. The sample is part of that population. It's some of the people or objects that you're interested in. For some reason, maybe you're not allowed to get all that data, or maybe it's impossible to do it. Well, sometimes you can use samples to sort of lean in the right direction, because this will give you an idea of what the population is really like. To do that, you just don't take any kind of a sample. You want a representative sample. You want one that resembles the actual population. Sort of like you take the population and you shrink it down to 1% of what it was originally. If it looks about the same proportion-wise, then you can draw some conclusions using inferential statistics. So let's look at some examples. We've got a group of hotel owners, and they want to know about what people think about casino gambling. Well, maybe they want to have some casino gambling in their hotels because that means more money. First, you want to describe the population. Who are you interested in? Well, it's all of the citizens of the city in this case. Part B, survey all the people at 6 of the largest nightclubs in the city and ask them what their opinion is. Does this seem like a good idea? And I'm going to grab this. Does this seem like a good idea? So you might want to pause this for a second, read through it one more time, and see if you go along with this. Okay, you're back? Well, nightclubs, really? Don't you think those would be more likely to be in favor of gambling? So that's probably not a good representative sample. What's a random sample? It's a sample that's put together so that every member of the population could be in the sample. How do you do that? Identify the elements in the population. What does the population look like? What kind of things or people are in the population? You can assign numbers to every element in the population. For example, if you've got 7,000 people in the city, just assign a number to each person. You're not calling them by numbers, but you're assigning them just to keep things straight, to keep things organized. Once you've got the numbers that are assigned to the elements of the population, randomly select those. There are a bunch of ways of doing it. Once you've got those numbers that are randomly selected, back up and get the elements in the population that were assigned to those numbers from the sample set. How could we do it with the casino gambling? Well, how about this? Randomly survey people that live in the oceanfront condominiums. Would that be a good idea? But they have an interest in not having a lot of traffic and noise, which would be what you'd see if you had a lot of nightclub or casinos involved. How about this? Survey the first 200 people whose names appear in the city's telephone directory. You think that would be a good representative sample of the people in the city? But not all the people have an equal chance. So that might not be a good idea. How about you randomly select neighborhoods of the city and then survey all the people in those selected neighborhoods? Yes, every citizen has a chance to be selected. Next, frequency distributions. How do you create a frequency distribution? Well, here are some numbers that we've got. We've got the date of the age of maximum yearly growth for 35 boys. In other words, how old were they when they grew the most when they were children? Now, these are not in order. Take a note of that. We've got 12, we've got 16 here, 11 here. They're all scrambled. This looks like raw data. So this is how you do it. First of all, take all those possible ages, make one column of those. Don't skip any of those ages either. If there are none in the 13 category, for example, put the 13 in there anyway, because that might give us an idea of what those growth spurts center around. Go in that data, see how many 10s there are. Well, if you look at that group on the left, there's 110 right there. Then you go to 11. See how many 11s there are. In this case, there are 2 11s. Next, how many 12s are there? There are 5 of them. And on down, 18, there's 1 in that group of boys. So there is our frequency distribution. Here are the numbers that we're interested in, and this is how many are in each of those categories. That is frequency distribution. These are the frequencies right here, and we've got a distribution of ages of maximum growth. So what can we say from that sample? Excuse me. Take a look at that again if you like. What can we say about that example? Well, we can see that most of the subjects had maximum growth between 12 and 15. 12 to 15. Most of those boys, as you can see from the numbers, were from 12 to 15. Also, usually goes from 14 and then decreases after that. So 9, 6, 3, it all goes down after 14. Here's another example. We've got statistics test scores for a class of 40 students. We've got 40 students this time, all listed here. Notice again, just for the record, these are not in order. 82 is here, but 76 is here. They're definitely not in order, but they're all there. Now, this is a second way of creating a frequency distribution. This is a grouped frequency distribution. To do that, we create classes, equal classes that are meaningful for the data. For example, we might take them by tens or fives. It all depends on the actual data itself. Since the letter grades go by tens, we'll take as our classes the 40 to 49 scores, 50 to 59, and so on up to 92. I think this should be 100, right, folks? So you set up your classes. Your classes are right here. We'll change this to 100. They'll never know, right? And then in each of those classes, you count to see how many of those grades were 40 to 49. Well, if you look back, you can see there are 3 of them. I'm not going back. In 50 to 59, there were 6 students in there, and so on. A good idea, too, when you get all these frequencies, add them up and see if you've got the right number. We had 40 students, and these add up to be 40, so it looks as though we're in pretty good shape as far as the frequencies are concerned. Notice that the way we describe these classes, there's a lower class limit and an upper class limit for each of those classes. It goes from 40 to 49, and we don't have any gaps between them either, notice. You don't want any of those grades to have no class to fall into. The class width is 10. How do you figure out the 10? Well, it's pretty simple here. One way of doing it is take 2 consecutive lower class limits and subtract them. 50 minus 40, that's 10. Or you could take upper class limits, 2 consecutive upper class limits. Well, let's go down here. Subtract those, 10. And that's your class width. Class width. These are the class limits. Lower, upper, class width is from one lower class limit to another, or one upper class limit to the other, and subtract the 2. Next, histograms or frequency polygons. We need a picture. The frequency diagram was really nice, but how about a picture? A picture is worth 1,000 words, correct? Well, definitely with statistics, that's very true. So, first of all, the histogram. One of the things to notice is that it is a bar graph, but with a histogram, the bars touch. So notice down here, this bar and this bar touch. Each consecutive one touches the next. That's one of the characteristics of a histogram. The frequency polygon looks a little bit different. It looks as though we actually start with a histogram. Well, that's not quite true, but close. As far as understanding what a frequency polygon is, it's good to think of a histogram to begin with. Now, with the frequency polygon, you take each of those bars and make a dot where the midpoint is at the top of the bar, like this. Once you've got those marked off, do one more thing. Back off 1/2 of a bar where there's 0 on the left side, and also 1/2 a bar on the right with a 0 on the right side. Then connect those dots from left to right, and there you've got your frequency polygon. Got that? If not, just back up the video and listen to it again, or read a description, or if you have to, go to YouTube and ask for how do you make a frequency polygon if you didn't follow what I said. Next, stem and leaf plots. Nice and simple, not too hard to make, and it's easy to get a picture of what the data looks like. What we do here is separate each data item into 2 parts. So for example, just to get started, suppose you have the number 58. What we do is we split that into 2 parts, the 50 part and the 8 part. This becomes the leaf, the lower part, and this becomes the stem. And we do that for each part of the data, and then, well, you'll see, we're going to put those into a graph. Stem is a tens digit, leaf is the units digit, like we had up here. And this was a 5, and this was the 8. Now let's get some data in here so we can play with it. Here's that data again. Notice the 82 up here, the 76 down there. Same numbers as we had for the statistics class, I believe it was. So you'll take each one of those. Now, for example, the 82, split that into an 8 and a 2. We'll put the 8 on the left side, the 2 on the right side. So enter the data items in the first row. Here's where we had the 82. Notice this was the stem, the tens unit, and this is the 2 for the units. That's the 82. Now let's pick another one. Let's say 63. 63 you can find 6 as a stem because that's the tens, and 3 as the units. Each one of these has a pair, and you can find that pair in a stem and leaf plot. You've actually got a real simple stem and leaf plot right here, but we need some more pieces. We only have some of these leaves here, so fill in the rest. The final plot is this one. Notice if you pause real carefully, you can see all of these entries up on the top here in this list. For example, this represents 47. There's our 47 up there. This is a 45, and you can find the 45 up there. There it is. You've also got a 43 from down here, and 43 is up there. There it is. Each one of these is taken from up here, split up. The stem part goes here, and you only put one number down for the stem because all those, it's separated by stems. And for each stem, you write down all the leaves and keep those in nice even columns. So what you end up with is a very simple graph, an easy graph too. And we're getting close to the end here. Deceptions in visual displays of data. How could someone try to deceive you? Well, take a look at these. If you look at this table right here, that's where all of this comes from. If you look at this graph and this graph, they both come from the same data. But look at the graphs. they give an entirely different idea. The graph on the left makes it look as though there was a steep increase and then a slight decrease the last year. The one on the right, which is done a little bit differently, it looks like it's pretty much flat. Nothing much happens, not much of an increase. And the reason it looks that way is if you look on the left here for the Y units, the Y units go up in different steps. Over here you have steps of 0.4. Over here you have steps of 2%. It gives an entirely different look to it. That's one way to lie with statistics or be deceptive with your displays of the data. So be careful. When you see graphs like this, be a little bit hesitant about making decisions unless you get a second opinion. So look for these. First, is there a title? There should be a title that explains what's being displayed. Are the numbers lined up with tick marks that clearly indicate the scale? You need to be able to see the scale. Has scale been varied to create a more dramatic or less dramatic impression, like we saw in the last example? Are there too many design or cosmetic effects? In other words, are there too many special effects that detract from the actual data and seeing what's going on with the data, how they're changing, how it's changing? And do you get the wrong impression because equally spaced time intervals are chosen on the horizontal axis, or have they switched things around? Does the time interval have a strange representation? Are the bar sizes scaled proportionately? Is there a source that indicates where the data came from? In other words, maybe you want to check and see whether the data was correct. You could go back if you have the source. Cosmetic effects can make things a little bit strange. So, for example, this data doesn't get represented properly here because even though you're going from 80 to 90 to 210, oops, this goes by 10 years, this goes by 20 years. That's not the way to do things. Another thing, notice that your eyes look at the area of this house versus that house. And if this actually is represented by the width of the house, the area is going to distort how big this has grown. Anyway, just some ideas for you. I want you to be critical of data you see and how they're represented. Well, next time we'll see a little bit more about how data is and how we can show it. Until then, you take care. We'll see you.